somebody would mind shutting the doors back there, please. And that way we won't bother anybody, maybe they won't bother us. Thank you. I'm KA2C, Kilo Alpha T Charlie. Good morning. Thanks for coming. No need to take pictures, except maybe of my site here where you can find the slides, some other information. I want to talk to you about 80 and 160 and dipoles and verticals. Simple ways to tune them. Simple ways to make them work very well. And so hopefully you'll have fun with that. Challenges, we all know this, 160 and 80, the antennas get big, okay? Big towers, lots of radial, big inductors for loading, and so forth. And that's a challenge for you. Unfortunately, another problem is the antenna bandwidth. And a lot of bands just kind of put up with limited bandwidth, or maybe they use a tuner in the shack. But some form of tuning is usually there. I mean, there are broadbanded antennas, but we want to talk about ways of doing this that give you good performance, very low SWR, and can allow you to really put out a good signal. You do see high SWR operation, coaxes running with 6 to 10 to 1 SWR. And that can cause issues with high voltages and high currents, of course. So some of the solutions that are out there, you can attempt to broadband an antenna. Usually that makes it bigger, fatter, higher. So you can do that, and but it's hard. There are a lot of bands to do that, to really broadband an 80 or a 160 well. And to make it smaller, which is usually the case, shorten it, of course the bandwidth gets even more challenging. So you see general purpose tuners. Some do remote the tuners, which is better than having it right on your desk for performance. A little harder maybe to do. What I want to talk about is special purpose tuners, or what I call integrated tuning, which is where the tuning is done right on the antenna elements. You have nothing between the tuning and whatever you're using to tune the antenna elements. And that means that there's nothing to provide any significant loss between that tuning and the antenna element. So that's one of the advantages of it. I'll show you some of the antennas I've built and used in my shack, which are multi-segment or binary step from 160 and 80. And it's very nice to be able to use the entire band, operate at full 1.5 kilowatt hour, and have a nice result without resorting to general purpose tuning. So some of the advantages are, of course, you can get full coverage. You don't have losses from balance. You don't have losses from SWR, from coax due to the SWR being high. Of course, you have the normal matched losses, but you don't have additional losses. And I can show you some results on that, which are quite interesting. You don't have to tolerate high RF voltages. Even at 1.5 kilowatts, you're only talking about several hundred volts when you're matched with 50 ohms. So you don't have thousands of volts to deal with in your system. Now here's a point. You can do this with really low-cost components and systems. It's amazing how inexpensive this can be, and I'll show you that. Now one of the key points is here, if you start with an antenna that's resonant in the band, top of the band, middle of the band, someplace near the band, then that simplifies this, and that's what we assume in this operation. So if you're talking about an antenna that's far from resonance, that's a different kind of a problem. Okay, so I'm not trying to solve that problem here today. I'm just trying to solve the problem of, I have an antenna, it's about where it needs to be, but I want to cover the entire band, and I want to cover it as power. Okay? So just a little bit about how the antennas behave that is helpful to solve this problem. This is actually the results from some ECNEC simulations. And I'm looking at the impedance of the antenna. This antenna is resonant at 4.0 megahertz. It's an inverted V. It's only about 40 feet up in the center, easy to put up. About 20 feet from the endpoints. Okay? So you have the antenna resistance, that is the real component of the impedance. And you have the reactance. And I plotted these two things across the band. And what do you notice? Well, the resistance goes down as you move down in frequency because the antenna is getting shorter relative to the wavelength. Okay? But it doesn't go down that much. It only goes down a little bit across the band. In this case, it's going down from about 56 to 36. So it goes down noticeably, but not by a huge amount. It turns out that if you match to a compromise match in the middle of that, the peak SWR due to that alone is only 1.2 or so. So you can pretty much ignore that if you do a compromise match. Okay. But the reactance, that's the imaginary part. Okay. In this case, capacitive, which is negative, because I've tuned the antenna to the top of the band, it's physically short to the rest of the band. So at the top of the band, 4.0 is 0. And if you went beyond, by the way, in higher frequency, you would go real, of course, become inductive. But at the bottom of the band, it's over 200, the reactance. So that's going to cause a severe mismatch, okay? And it does. If you don't do anything with that, your SWR will be about 6 or 7 to 1 bottom of the band. Okay, not so good. So, if we merely compensate for the reactance, which all that requires is some loading coils, guess what? We can have an excellent match across the entire band. And that's what we're going to show you. In this case, I simply have 8 binary steps across the band, 3 inductors at different half-step values, and switch them in and out. And it produces a very nice result. Here's a picture of 1.5 kilowatt tuning box for this. And really what I did was I replaced the balun in the center of the antenna with this box, which is about 5 inches by 6 inches. It has 3 loading inductors. They're T200s, 2 inches in diameter. They're a number 2 mix. And then there is a FT240-43, which I use as an Aug transformer or balun at the input. The turns on that don't have to be 1-to-1. The windings are intermediate, of course, to maximize the coupling, minimize losses. But you can, for example, in my case, I have 8 turns on the primary and 7 turns on the secondary. That lowers the impedance down to about 40 ohms at the output. Okay. Provides a nice compromise match across the band. This was, I took a small PC board. You don't see them, but on the underside of that board, there's 3 small relays. Okay, they're about 1 inch by ½ an inch by 3/4 of an inch tall. And this is what you typically see in antenna tuners and antenna switches. So they're rated. I'll go into relays a little bit later, show you some information about relays that are good for this purpose. But they can handle about 1 kilovolt of voltage in the open contact position, and they can handle 10 to 20 amps of current. Okay. So to control this thing, all you need is 3 wires coming in, and I'll show you how that works. Very simple. I have a 4-wire cable coming out from the shack for this thing, and a little switch to control it. You have a question?
Yeah. What's the weight of this unit, and how high is it?
Oh, it's in the center, in place of the balun. Weight-wise, 1 or 2 pounds. It's pretty light. It's light enough I didn't worry about it. I just pulled it up with a pulley and a rope, and it's quite light. It weighs a little more than a standard balun, I'd say, but not a lot.
Yeah.
Yeah, good question. I mean, if it's reasonably nailed down on your tower, I don't think you'll have a wind problem, barring severe winds. Yeah, maybe a little tough to see. These are the SWR sweeps of the 8 steps across the band. And at the bottom of the band, you can see you can get to about 1.5 at every step across the band. Okay? Down here at the bottom, where the match of the resistive part of the antenna is not quite as good, you can see that it bottoms out about 1.35. Okay? And so between the two adjacent resonant points, you go up to about 1.6 or so, but still, you're quite a good match. At the top of the band here, the SWR goes down to very close to a 1-to-1. So you can cover the entire band with this little box and have excellent matching out at the antenna so that your coax and your other components see very nice low as medium. RF transformer, which also serves as a balun in this case. The primary is unbalanced. The secondary is balanced, or close to it. It is a transformer. It's not a current balun. But the efficiency is quite high. It's in the high 90s. And we haven't noticed any warming or that kind of problem. This is each of the 3 relays and the 3 coils. So, quite similar.
Could I ask you a question?
Yes, sir.
I hope you don't mind me stopping.
No, it's fine. Please. Questions are good.
So why did you choose? I can understand how you use 8 to 7 after the weeks.
Right.
Where you wanted it.
Right.
So 8 to 7 is pretty close to 1-to-1, so that's kind of like a nice division.
Slowing a little bit. Yeah.
Why don't you choose T200 or T2 mixes for your other?
Oh, okay. Okay. Yeah. So a variety of information sources, of course, that you can find books as well as sources on the web. If you look at recommended frequency ranges for inductors for different mixes, T202 is recommended for 3 to 30. There's also mix 6, which I think could be used, but it's maybe a little higher in frequency. So either one would probably be fine for 80 meters. If you go to 160, you may prefer the number 2 mix. But either one is probably going to be fine. You're going to be only small differences in performance. Now the balun is a 2.4-inch core BFT 240-443 mix is very commonly used in baluns for the HFBs. It's usually up to the 10 meters as well, although when you use at the higher frequencies, there are other mixes which you could use there as well. Yeah, another question.
If you lower the center now, if you lower it to 36 feet, do you lower the ends also about 10%?
Not necessarily. No, there will be a slight distinction that will happen in the impedance and in the bandwidth, but it'll be, for small differences, the differences will be small. Okay, but having said that, it's always a great thing to put this thing in ECNEC or one of the other simulators and see what happens. Okay. So I use ECNEC extensively for this kind of work, and recommend you try that if you want to do some simulation. This is a controller. Simple enough, right? 12-volt, very simple power supply, very basic, and a 3-pole 8-position switch. So to select your frequency, it's just tune it across the band to the right resonance with this very, very simple controller. Okay, any questions on that dipole or / inverted V? It could be a dipole, of course, but I chose the inverted V, which has some pluses from one support, somewhat more omni pattern, and so forth. Third V does have slightly lower impedance than a typical dipole, just a comment in that way, and a slightly reduced bandwidth also.
So any adverse effect when you go higher?
Well, to go higher, the issues, typically the bandwidth will actually increase. So now, you probably get better performance in general. it might be slightly less omni, although if you use a inverted V shape, that'll tend to offset that. Okay. So let's talk about verticals. What are the questions? It's available online at my website. I'll go back to that at the end. But the whole thing is on the web. It's my website, www.ka2c.com. And I have a page for antennas. Okay. My high tower, which I put up a couple years ago, 36 radials, buried about 6 inches. And, you know, high tower, I mean, you're spending a couple grand, spending a lot of money, and you put it up and, what, you get 150, 200 kilohertz coverage? Kind of disappointing, right? Furthermore, I put this thing 250 feet from my shack up on a ridge. So I had to run, what, coax. So you don't want to, and I can show you this, you do not want to be running highest WR on that coax. Certainly not for 250 feet. So it was important to go with tuner. The tuner costs much less than the antenna. Okay, so why not tuner? And by the way, as a comment, if you look at systems that are in the market out here that kind of use this kind of approach, one of the places that uses this are the guys that build the 80-meter Yagis. Okay, now think about this. You spend 50 grand, 100 grand, whatever it costs to put up an 80-meter Yagi, and you get 100 kilos of hammer. Very disappointing, right? This almost identical technique is used by Array Solutions and by some of the other guys that actually built some of these humongous 80-meter antennas. So if it's good for that, it's good for, you know, a couple $100 dipole, right? Okay. I found this very simple technique to use a off-the-shelf remote switch. I didn't want to run a control cable at 250 feet. Okay? And I had conduits that was buried. It's a lot of work to get a cable out there. Plus, I just didn't want to bother. So I bought off the shelf an RCS-4, brand new, for about $230, $240, I forget the exact price. And I made it work to step across the beam. I could have done it in 4 steps, but I decided 3 steps was enough. This is, I took the cap off and I wound 2 inductors with T200-2 cores again. They're fine to handle full power. And I made 4 solder connections. And I put the box back together. And that's what I got. Simple as pie, right? So I have 3 nice steps across the band. Now in this case, the minimum or the worst case SWR is about 2 to 1. Not quite as low as with the previous antenna, but still quite respectable. And if you go through the calculations with one line calculators, it turns out that if you've done nothing, you would have lost about 3 to 4 decibels in the coax due to the highest WR, beyond the baseline loss. Okay, so you have an additional 3 to 4 dB of loss. By doing this, the worst case loss in the coax, the additional loss through the SWR, is only about 0.4 decibels. Okay? So you take a 4 decibel problem and turn it into a 0.4 dB, almost negligible. Okay? Of course, in the shack, you know, if I run barefoot with the antenna tuner and really cleans it up, or with an amplifier. But the low SWR, the 2 to 1, pretty much elimination of flex in this case. Again, I'm running 250 feet. The cable is very flex in this case, similar to LMR 400. You know that. Yes, question.
It seems like it might be worthwhile to use 4 inductors and use a full capability.
Yeah, I was just lazy. You're right. You could make this better. You could even use 8-step tuner, but with a little custom getup than I had, and get it down to 1.5 across the band. With the RCS-4, you would be limited to 4 steps though.
Well, that's what I was thinking. There's 4 switches.
There are. You could probably get it down to about 1.75, 1.8 with 4 steps. But I chose to stop this. Yeah. Other question? Okay. Just wanted to comment, you could actually use an RCS-4, a lot of text I don't know if you all see here. You could actually use an RCS-4 with a dipole, an inverted gate as well. It takes a little more work than with a vertical. I did want to show you this dual band antenna. Actually, this is an older antenna that I built. I did on 11680, and I wanted to cover the full band and have a well-matched high-performance system. So I built this box where I had 4 tuning segments across each band. You can see the here's the T200 loading coils, and they were wound separately for 160 and for 80, and they're binary step together. So when 160, one inductor would move you from near the top of the band to the middle of the band. The other inductor would move you about a quarter of the way down, and you put both in there, and you get about 3/4 of the way down toward the bottom of the band. Okay. Another comment about this is, if you are driving the dipole inverted beam near the center, it turns out the impedance changes very slowly as you go off center. That's different from an off center fed antenna that we're normally used to. It's 1/3 or 2/3 length, or even farther out. In that case, the impedance tends to change fairly rapidly as you move away from a drive point. But in the center, the impedance changes quite slowly. Okay? That's important. Why is that important? Because you do not have to be perfectly symmetrical with your loading. And if it's in the center, to shift you around inside the band. If you load on one side only, which is what I'm doing here, I have one inductor on one side of the antenna, the other inductor on the other side, and you have independent relays to switch them in and out. Because you're at the center of the antenna, the effect on the impedance by being slightly off center is negligible. Okay? Does it make it slightly asymmetrical? Yes. But it's very small amount. Okay? Control unit, yes sir.
What's surprised that you wanted or you found impedance at the lowest band full size?
Yeah, this was slightly less than 40 feet from the center. On 80 meters, it was probably in the 40s, 40 to 50. And 160, the wavelength above ground is quite low, okay? That will lower the impedance of your antenna. Okay. So in that case, I used an arc transformer. This is the control unit for this particular device. 8 steps. I at one point had a remote control feature where the 8 wires controlling, or the 4 wires controlling the relays could be controlled by my PC, in which case I have a team viewer and I can control that and so forth. But I eventually can use that. Let me show you. Let me show you this loss thing here. For my vertical, my high tower, 250 feet out over coax, what happens if you actually don't match it out with the antenna? As you can see, I have 250 feet of coax put in. It's selected Davis Veriflex. And now, 4 megahertz. The resistance is assumed matched at 50 ohms. Probably not quite that, but okay. In this case, I selected a reactance of minus 46. 46 ohms, minus 46 ohms. Reactor. And you can see the SWR comes out to about 2 to 1. Well, if you look at the loss here, the loss of the coax is only about 0.7 dBs if it's perfectly matched. You have an additional loss of 0.33 dBs due to the SWR 2 to 1. So you have a total loss of just over a decibel. Not bad for 250 feet. Now, suppose I didn't match out the antenna, and I tried to operate at 5 or 6 or 7 to one SWR at one end of the band, and I tuned it in the shack. What happens? Well, we'll put this reactance up to minus 250. Take a look. Wow. Okay, the SWR went up to about 7.8 at that reactance, okay. But look what happens to the loss. Yeah, the baseline loss is still 0.7 decibels. But the additional loss, 4.6 dB in this case, I'm up to 5.4. So how disappointing. I bought that expensive tuner, I have it sitting next to my amplifier, and I'm losing 5.5 dB. You don't have to do that. Notch your antenna a little closer to the elements. Okay?
I didn't hear the last comment.
Okay, yeah, I was just saying that by matching the antenna at the base, out there, remote, the SWR on the coax is now more friendly, 1.5 to 1, 2 to 1, in that range. And now I have tenths of a dB kind of losses additional due to the SWR instead of 4 or 5 decibels, which is significant. 4 or 5 dB is taking your QRO situation and almost making it there for the end. Okay, this is the SWR results that I had with this 160 80 meter inverted V, which had 4 steps. It came up to about 2 to 1, maybe even a little higher in some spots, but it did allow me to tune across both bands with fairly modest SWR. And it cleaned up the tuning, of course, in the shack with the rig as well. There's 80 and 160, the results that I had. So you can see the 4 resonant points a little better here in 160. 180, I think one of my inductors was actually, the step size is not quite right. You can see that it's not a nice linear step. So I never bothered to fix it. But that was the result. So, some comments about this kind of a simple way of getting full bandwidth in 160/80 for your vertical or your dipole. It works best if you have full size or near full size antennas. You can take a shortened antenna and put an external loading element or some other pre-matching system, and then maybe make this as the next step in your matching. That is possible. But this does work best with full size antennas. It works best with center fed dipoles, inverted Vs, or verticals. You're working in a place where the impedances are friendly. There are 50 ohms, plus or minus. And so you're operating with currents and voltages that are not extreme. But there is a question about the relays, and I want to get into that a bit. I talked about easy MDC. It really helps to not be shooting in the dark when you do a project like this. You can determine the loading coil sizes that you will need. The MDC does support putting in loading coils. Of course, the actual structure of the antenna itself will be part of the simulation. The remote control part can be a little challenging, I would guess, for some, but again, back to that issue, you can take something like an RCS-4 and modify it. If you have more relays than that, a cable that has 3 or 4 wires or a few more can do an awful lot with a system like this. Okay, relays. Well, vacuum relays are used in some systems where you have high voltages typically, but they're expensive. There are a few sources, but it can also be a bit fragile. So I try to avoid them. You also have, fortunately, very inexpensive relays that have been developed for AC power stations. Typically, they're rated at 16 to 20 amps, kind of current that you have on a single circuit. And they typically have breakdown voltages rated at about a kilovolt, but that kilovolt is for 60 hertz. Okay. So unfortunately, finding relays, except for special purpose ones that are particularly made for RF, these relays, there typically is no RF kind of information available. It's unfortunate, but that's the way it is now. So the folks who design antenna tuners, design the switching inside the rigs and so forth, have generally figured out how to deal with that. But for the average ham, information about this is a little limited. Well, if you do some investigation, one of the things you'll find out is that in the HF range, there's a theoretical lab work done that comes up with numbers like 0.8 as a factor for the arc voltage breakdown of open contacts. I want to be clear, we're not talking about breaking a live circuit. Okay, that's a whole different kind of a thing. For RF, you will get a corona if you try to take a hot circuit and break the relays. And the actual, that'll keep the circuit live for a large gap, and it's hard to break significant high current RF system. So we're only concerned here about switching when it's dry, when it's not active, and then what's the breakdown that you can handle once it's in that position. But anyway, these relays can handle about 1,000 volts at 60 hertz, so they can handle about 800 volts of RF in the high frequency range, 3 to 30 megahertz. Current is a different issue. The issue with the RF current, part of it is skin effect. So you will find that as you go from 3 megahertz to 30 megahertz, the current capability of these switches will start to droop. But again, no published information typically in these switches. So what do you do? Well, looking at various sources, the rule of thumb might be about half the current at 3 megahertz, maybe only about a quarter of the current at 10 megahertz. I'm sorry, 30 megahertz, 10 meters for these kinds of switches. So if you have a switch that's rated for 20 amps at 60 hertz of this kind of a switch, and you're trying to use it at 10 meters, think 5 or 6 amps. Now, fortunately, that is about 1.5 kilowatts at 50 amps. So that's why these switches are okay at 30 megahertz for full power, but they're right on the kind of the edge. There's no other margin. Okay. Let me blow this up again here. So I decided to actually do some investigation of some switches and see what I could determine, including cutting them apart and doing a teardown. And this stepper is very similar to what you typically see in antenna tuners and remote RF switches and so forth. It's rated at 20 amps and 1,000 volts. But when I actually measured it with a tester that I bought, which I'll show you, it was almost twice that. Now, there's a couple reasons for that. One is I was near sea level. Okay? Now, if you know about relays, if you go up in altitude, a strange thing happens. The breakdown voltage goes down. In fact, there's a point at very thin, very high up in altitude, where the breakdown is incredibly lower than it is at sea level. Okay? It turns out this is not a major factor for hands because at 5,000 to 10,000 feet, you lose about 0.8 to 0.9, but it is something to consider. If you're at 10,000 feet, parts on the air, and your tuner starts arcing over, there may be a reason for it. Okay? Anyway, that's so the manufacturer built in some margin because they actually spec this stuff, I think, at like 5,000 meters, or a couple thousand meters in height. So measuring the sea level, that is a factor. They also build in some margin naturally. But there was another reason for this particular switch. They built these switches in single pole double throw variety or double pole double throw. They also build them in single pole single throw. Turns out if you open them up and look at them, everything is the same in these two cases, except that in one case, the set of contacts just disappears. What does that mean? Well, that means that there's nothing there for the contacts in the middle, which we have to press against, to actually physically go to a flutter. And so you actually get a higher voltage rating out of a single pole switch in a particular family line than a double pole is. That's also a factor which I learned from looking at these things. It turns out that the solar push, the green efforts, has caused industry to develop new sets of specifications for switches to handle the higher currents, in some cases higher voltage in solar systems. So there now are a different class of family of switches from the ones which we see for home use that have been developed for solar systems. And because they're in high volume, they produce them at low cost. So that's where this next one comes from. This one here is rated at 33 amps, so it's a little bit higher than your 20 amp house circuit. It's also rated at higher voltage. And with the tester, I measured up to 3.8 to 4 kilovolts. That's getting more interesting in terms of ability to handle the voltage across larger coils. Okay. There are even larger power switches. This is more like a contactor here. And this thing was a double break. I'll show you a picture of it, but it can handle even higher voltages. Now again, these things are fairly cheap. This last one here is a little more expensive, $10 to $20. But this one in the center here is only a couple dollars still a piece of this relay. Okay, if you decap one of these relays, do a tear down, look inside, that's what you see. Contacts are not that far apart, okay? Pretty close. And well, if you go and do some reading on this, they don't have to be that far apart. It turns out that you get about 30 kilovolts per centimeter breakdown, okay? Well, so a gap of 0.7 millimeters gives you about a kilovolt, okay? But there's some good news here. Compared to old relays, the open frame relays that we're used to, if you look at the lengths of the leads inside, they're quite short. That's good, right? It looks like it's copper-coated spring steel. Okay, it's obviously not pure copper because of the springiness. Okay, and they actually have quite nice wide conductors. So the inductance of the leads on these newer relays is quite attractive. The contacts are typically some form of silver. Now that can be an issue because they will corrode a little bit over time. So if you don't put power through them on a somewhat regular basis, at least every few months to a year, that can become a problem. So you don't use these in your seed systems, just to make that comment. But if you plate them with gold, you have a different kind of problem. So anyway, let's keep that in mind. So this here is the larger solar industry kind of relay that I found, which is still an inexpensive kind of relay. But you can see the gap here is bigger. It's close to 2 millimeters. Okay, so that's consistent with the 3 to 4 kilovolts kind of breakdown voltage. And it's interesting how on the power pin here, you see that it fans out like a triangle to minimize the inductance and the current carrying capability. So it's just interesting to understand how these things work. So this was the much larger one. Turns out it's what you call a double arm kind of relay. There's 2 sets of contacts, and in the middle there's they call it a double break. There's a moving arm. So you don't need something that is a spring because everything moves. Now, you would ask yourself, if I put two relay contacts in series, does the breakdown voltage double? Okay. I asked myself that question, and it wasn't so obvious to me what the answer was, and I thought, well, the answer's not so obvious, so probably not. Actually, it turns out that even with RF, that the breakdown voltage generally tends to kind of double in practice. And I won't attempt to try to explain the physics behind that, but it seems to be the case. And you would think, well, okay, if there's a little error in the capacitance, the stray capacitance, and the stray resistance between these things, they would become unbalanced. But it doesn't seem to. And in fact, if you tear down some of the tuners that are out there, in some places they actually use multiple relays in series to get a higher breakdown voltage. So commercially that is done as well. But anyway, in contactors and in the higher current, higher voltage relays, you'll see this double break kind of architecture because you're not relying on a still spring contact. How to test 5 and 6 kilovolts? Well, very carefully. You've got to have a set of rules, write them down. You'll have a bad day if you don't. This is a tester. It was a couple $100. And I was interested in how these relays would actually perform. It's 60 hertz, okay, only. So it doesn't test for RF, but it will go up to 6 kilovolts. So that's kind of interesting. I got myself a 2-inch PVC pipe, kind of about 2 feet, and used it to control everything when this thing is plugged in and on. Okay? So it doesn't work in every test situation, but it worked for this one. We hit an off for the voltage. I was simply twist it, turn the voltage up till the tester informed me that it was breaking. But anyway. You're going to test that, you're going to touch that thing, you unplug everything. That's it. That's it. I ran the tube with one hand. Anyway, it is possible to test relays for 60 hertz like this, up to 6 kilovolts with a fairly inexpensive tester. How to test an RF is a different issue, different talk. Okay, something about the loading inductors for this kind of a system. You're only loading the antenna by a somewhat incremental amount. You're not putting a large loading coil. You're like trying to make a 43-foot vertical work 160 meters. That's a big loading coil, right? And that's a situation where the impedance is very low. The resistance of the inductor should be very low if you want to have a signal. In this case, you're operating 25 ohms, 40 ohms, 50 ohms kind of antenna. So it's not necessary to have inductors with very, very small internal resistances or very high speed. So these T200 cores are perfectly adequate. There's very, very little loss in them. You can try to simulate that or calculate it, but it's pretty much not something to be worried about. I use 14 gauge wire. You could use 12 if you want to try to minimize the loss a little bit, but it's not going to make that much difference. You asked about the cores. The -2s are good. If you really are concerned about how high power, you could potentially stack 2 of these. But for the kind of inductance that we're adding here, 1.5 kilowatt should not be a problem. Here's some sources. Kits and Parts has, first of all, they sell these, good price. That's where I buy my cores. They have a calculator there which you can figure out inductances, turns, that kind of thing. So I make good use of that. Now when you get to core heating and saturation, it's a little more interesting, a little tougher. Actually, full information tends not to be available. There are examples. The calculations are a little more complicated. But if you go to Ameritron Core, they have a series of papers and documents there which will give you guts and guidance. So you can at least become ballpark in what you're dealing with. Okay. I wanted to just point this previous related kind of work. I mentioned array solutions. They're 80-meter Yaki uses a very similar kind of technique to step across the band. Of course, with a Yaki, you step not only the driven element, but you step, of course, the reflector and the driven element. I'm sorry, the director. But there's a nice paper here by Grant Saviers. It was in QEX. It's also in the new ARRL antenna book, I think in the X-rays that they include there. He had a 160-meter antenna, vertical, that was full size, using trees out in Washington State, big tall trees. But he was a CW guy, I think, so he tuned it at 1.825 or something. Okay? And after a couple of years, he was like, well, I've got this giant antenna, and it's no good at 1.95, unless I want to just tolerate the highest of the mark. And I guess he started hosting some contests with some friends, and they said they wanted to phone him. Anyway, so he decided to fix the problem. Now, in his case, his antenna was tuned at the bottom of the band, unlike the examples I showed you. So when you go to the top of the band, the antenna looks inductive. So he used capacitors in series with the antenna to load it capacity. They were big capacitors. They were 5,000 bucks, 10,000 bucks, that kind of thing. And they didn't have to be extremely high voltage because he was operating at 50 ohms. So they were probably 1,000 volts to 2,000 volt kind of capacitors. Not trivial, but not 10,000 volts, something like that. Okay. So he, I think, he had 4 steps across the base. Very nice solution. I mentioned Icom, but also Optigame and others do a very similar thing. Here's one of the only low-end products from like a Dipole I could find where people have made a product and sold it. It's actually a European group that sells this thing. And they just support 2 frequencies. They call it a CW, a single sideband step. But they have relays out there in a little box very similar to what I showed you for an inverted B. And you can select 2 frequencies. Now, it'd be nice to add another relay or 2 and just tune the entire band, but they don't. But anyway, it's one of the few low-end commercial products you might have. Now, of course, there are other solutions out there, but it's interesting that there's not a lot of commercial solutions you can buy for simple antennas that will do this for you. Okay. So, 160 and 80, the bandwidth is almost always a problem for hams. There are very simple solutions which you can put out there. Some as simple as buying an RCS-4 in those box kind of tuners and a couple of inductors and setting up a number of segments across the band. It's a convenient place to put these. Just put it in the center unit of the dipole instead of the balun. We're right at the base of the vertical, so the placement is not a problem. If you need more relay controls, and you can support by the kind of control that an RCS-4 does, control cables for this, you're only running 40 or 50 milliamps for relay for the 12 volts. So you can use 28 gauge wire kind of control cables. And I mentioned modifying remote switches.
Sorry, you said 28 gauge wire cables. Your length is about 250 feet.
Different antenna. The 250-foot high gain is where I used the RCS-4, no control cable. Okay. In that case, you might want 24 gauge or something like that. You know, for 100 foot or 150 foot, somewhere in that range. Look at the
drops.
a little bit. Look at it. Do the calculations. How many ohms to 100 feet, and go through the voltage drop. But the point is, the current draw of these relays is very modest. So you don't need very large wire, but you should do the calculation. Any other questions? Okay, let me just go back and show you where the slides are, and then we can take some questions.